right, let's take a look at example 2. After a person drinks a cup of coffee, the amount of coffee in the person's bloodstream is 30 ppm. Suppose the amount of caffeine decreases or decays at a rate proportional to the amount remaining after 4 hours, there are 14 ppm left in the bloodstream. How many hours will pass until there are 10 ppm left in the bloodstream? So this might not sound like population growth, but it really is. And what gives away is this rate proportional. So we know we start with the exact same model. So we have our dp dt is equal to kp. And honestly, for the sake of time, let's skip all of the work we had from before and let's jump straight here. So we know that the population is what? Some constant times e to the kt after solving our differential equation. We know then our initial caffeine, right, to start is 30 ppm. So we know that P of 0 is equal to C e to the k times 0 is 30. That is C times 1 is 30, or the initial constant is 30. So we have P is equal to 30 e to the kt. Now, we also know that after 4 hours, we have 14 ppm. So P of 4 is equal to 30 e to the k times 4 is 14. So that is 30 e to the 4k is 14. Let's divide both sides by 30 so we can solve for k. We get e to the 4k, and then let's reduce this by 2, so it's 7 over 15. And then we'll natural log both sides, so 4k is equal to the natural log of 7 over 15, or k is equal to 1/4 ln of 7/15. Now, just like before, let's take this information and let's resubstitute this back in here for k. So we get our P of t is equal to 30 e, k is 1/4 ln of 7/15 times t, and then let's rearrange this so we can write this in a better form. So we have 30 times e to the ln of 7/15 all raised to this t over 4. We're going to join those together. Just like last time, we see that e and ln cancel, so we're left with 30 times 7/15 to the power of t over 4. And this here will be our population model for caffeine. Now, what's nice is it's very easy to check that our model works simply by using the calculator, right? So our model was suggesting that 30 times 7/15 to the power of t over 4. Now, we knew that at 0, it should come out 30, and as you can see here, it does. And then at hour 4, it should come out 14, and then you can see it does. What's nice is we can change this to any hour. So 1, 2, 3, 4, 5, 6, 7, and so on. And we can watch that caffeine slowly disappear